Same reranker quality, dramatically lower latency Quantization is the missing step. By the end, you'll understand how to turn a cross-encoder into an INT8 ONNX model that runs much faster while keeping the same top result. I'm Professor Pi, teaching search and IR with simple Python. Cross-encoders give great accuracy, but they are slow at re-rank time. You score a pool of candidates with a heavy model, and that cost shows up as latency. In production, that means fewer queries per second and higher infrastructure cost. Quantization folds model weights down to smaller numeric types, so the runtime can use faster integer math and smaller memory. Intuitively, quantization is like switching from wide paintbrush strokes to a thinner one that still follows the same pattern. ONNX is a portable model format. Together, they let you export a trained score, compress it, and run it in many runtimes with fewer CPU cycles. The trade-off is small numeric shifts that usually do not change which document ranks first. We will build a tiny linear reranker, export it to ONNX, time the float version, quantize to INT8, retime, and then produce the final re-ranked output. You will see how the same top candidate survives quantization while the model runs faster. Now, we will build the tiny re-ranking setup. This snippet creates a tiny, reproducible re-ranking setup with simple features and scores. The array docs holds 4 candidate documents, and the matrix X represents toy pair features for 1 query against each doc. The vector W acts like a cross-encoder projection, giving more weight to later feature dimensions. The expression X at W computes 1 relevant score per document, and argmax finds the index of the best item. Because np.random.seed fixes the feature values, the same document will win every run, letting us compare changes fairly later. The printed top index shows which candidate currently ranks first and anchors our baseline ranking. You can think of that result as the baseline label for the rest of the exercise. The next step is to package the exact same linear math into an ONNX model so the runtime sees the same operations. Next, we package that scorer into an ONNX graph. This example packages the simple linear scorer into an ONNX graph. The call onnx.helper.makeNode creates a matmul node that multiplies the input features named X by the weight matrix W to produce Y. The helper makeTensorValueInfo declares input and output shapes so ONNX Runtime can validate them. The weight initializer is created from the NumPy vector W and reshaped to a column, matching the feature dimension of 8. Finally, makeModel wraps the graph into a ready model object. The printed count of 1 operation confirms this ONNX model is just a single matmul, which is perfect for fast runtime and quantization. That ONNX model is small and deterministic. Next, we want a timing baseline for the full float path, so we have a fair comparison point before we touch quantization. Now we will measure float baseline latency. This code measures float32 baseline latency using ONNX runtime. The model M is saved to ce.onnx, and ort.inference session loads it for execution. The variable t0 captures a high-resolution start time, and ses.run executes the graph 50 times using the same feature matrix X for a stable average. The average per call latency in milliseconds is computed by dividing the elapsed time by the number of runs. Increasing the number of runs smooths variance, but lengthens the measurement window. Fewer runs will be noisier. The printed base MS shows your current per batch latency, which we will compare against INT8 to quantify speedup. With a stable float baseline, we can now apply dynamic quantization and see the wall clock change. The important part is to keep the same inputs, so we compare apples to apples. Next, we quantize the model to INT8 and measure runtime. This snippet converts the float model to INT8 and times it with ONNX Runtime. The function quantizedynamic creates ce.i8.onnxx with two int8 weights, targeting matmul for efficient integer execution. A session options object, S, is configured with ORT enable all to apply aggressive graph optimizations when loading the quantized model. The loop runs qsess.run 50 times on the same features X, and the mean latency INT8 ms is computed similarly to the baseline. Raising optimization level can reduce runtime further, while lowering it may increase latency. The printed speedup compares baseline to INT8, showing how much faster quantization plus optimizations makes inference. At this point, you will usually see a clear latency improvement. The next step is to confirm that quantization did not change the top right document in our reranker. Finally, we run the quantized model to produce reranking scores and pick the winner. This code uses the quantized ONNX runtime session to produce final reranking scores. The call qsess.run executes the model and returns an array for y, which is flattened into yq, so each entry corresponds to one document. The variable idx selects the highest score, best picks the winning document text from docs, and score shows its value. Because quantization preserves the linear structure here, the top result typically matches the float model while benefiting from lower latency. The printed best and score confirm which candidate wins after INT8, demonstrating a fast, end-to-end re-ranking selection suitable for real retrieval pipelines. To map this toy example to a real system, replace the tiny feature matrix with embeddings from your cross-encoder and feed batches of candidates per query. Use the same save, quantize, and measure flow to get production estimates. If you use CPU only, quantized weights and ONNX runtime optimizations often cut latency and memory use, letting you serve more queries per machine. Recap. What it is: a portable way to compress a reranker and run it faster with ONNX quantization. When to use it: when re-ranking quality matters, but CPU latency and cost are a bottleneck. One caveat: quantization can introduce tiny numeric shifts and should be validated on your data. Next step: scale this test to a larger corpus and add timing and accuracy checks so you can choose the right trade-off for your workload. If short, practical IR helps, subscribe and watch the IR videos.